Hi there. In this interview, we are focusing on chaos engineering and failure injection. This is not about breaking things randomly. It is about intentionally introducing controlled failures to understand how your systems behave under stress. If you are preparing for a DevOps, SRE, or platform role, this is a topic that separates people who know theory from people who have operated real systems. As always, I want you to pause after each question. Answer it out loud, think through your reasoning, then compare your thinking with the sample answer I provide. That is where the real learning happens. If this format helps you prepare for real interviews, subscribe so you do not miss the next simulation. Warm-up behavioral questions. First question, tell me about a time when something failed in production and you learned from it. Pause here and answer. A strong candidate might say something like this. In a previous role, we had a payment service that started returning intermittent 500 errors during peak traffic. Initially, we assumed it was just load-related, but after digging deeper, we found that a downstream dependency was timing out under high concurrency. The real lesson for me was that we had never tested the failure mode of that dependency. We only tested happy path scenarios. After the incident, we implemented synthetic failure tests in staging, where we would simulate slow responses and hard timeouts. We also added circuit breakers and proper retrees with backoff. That experience shifted my mindset from assuming systems will work to assuming they will fail in unpredictable ways. It made me much more proactive about resilience. Second question, have you ever pushed back on a risky change? How did you handle it? Pause here. A strong answer could sound like this. Yes, I have. There was a proposal to migrate a critical service to a new database engine just before a major marketing campaign. Technically, it was feasible, but the timing was risky. I raised concerns not about the migration itself, but about blast radius and rollback complexity. I suggested we either delay the change or run a shadow deployment first to gather real performance data. I framed it in terms of risk management rather than fear. The team agreed to do a phased rollout with traffic mirroring. That experience reinforced for me that resilience is not just technical. It is also about timing and communication. Third question, how do you create a culture where people are comfortable running experiments that might fail? Pause and answer. A strong candidate might say this. I think it starts with psychological safety and clear boundaries. If people are afraid of blame, they will never inject failure intentionally. In my teams, we treat experiments as learning exercises, not performance evaluations. We define guardrails before running any chaos test. For example, we decide the maximum allowed impact, the rollback steps, and who is monitoring. We document findings in a neutral way. Over time, this builds trust. Engineers start seeing failure injection as a tool for resilience, not as reckless behavior. Core technical and scenario. Questions. First technical question. What is chaos engineering, and how is it different from just load testing or staging testing? Pause and answer. A strong answer might go like this. Chaos engineering is about intentionally introducing controlled failures into a live or production-like system to validate resilience assumptions. Load testing typically focuses on scaling under expected traffic patterns. Staging tests often simulate idealized scenarios. Chaos engineering, on the other hand, deliberately targets failure modes such as instance termination, network latency, packet loss, or dependency outages. The goal is not just to see if the system handles load, but to see if it degrades gracefully when components misbehave. It is about validating hypotheses like, if this node dies, the system should reroute traffic within a certain time. It shifts the mindset from testing functionality to testing survivability. Next question. You want to introduce failure injection in a company that has never done it before. How would you start? Pause here. A strong candidate might reason like this. I would not start by randomly killing production instances. I would begin by identifying critical user journeys and mapping out dependencies. Then I would choose low-risk experiments, ideally in staging or in a small production slice. For example, I might simulate a single pod failure in a Kubernetes deployment to validate auto-healing. I would define a clear hypothesis before running the experiment. For instance, if one replica dies, traffic should continue with no user-visible errors. I would ensure observability is in place so we can measure the impact. After the experiment, I would run a retrospective to capture insights. Over time, I would gradually increase complexity, such as introducing latency between services or simulating partial outages. The key is incremental adoption and strong communication. Another question: how do you decide which failure scenarios are worth testing? Pause and think. A strong answer might sound like this: I prioritize based on impact and likelihood. I start with single points of failure. If a service depends on one cache cluster or one database, that is a candidate. I also look at historical incidents. If we have seen timeouts due to network saturation before, that is a realistic failure to simulate. I consider business impact as well. If a failure in the checkout flow costs revenue, that path deserves more resilience testing. I also factor in complexity. Some distributed systems have emergent behaviors under failure, such as cascading retries. Those are worth testing because they can amplify minor issues into major outages. So I combine risk analysis, historical data, and business priority to choose experiments. Next question. Suppose you inject latency between two microservices and user error rates spike dramatically. How would you interpret that? Pause and answer. A strong candidate might think through it like this. First, I would confirm the latency injection is the actual trigger and not a coincidental event. Then I would analyze whether the spike is due to timeouts, retry storms, or resource exhaustion. Often, added latency exposes tight timeout settings or aggressive retry logic. If each service retries 3 times without backoff, latency can multiply traffic and overload the downstream service. I would examine logs, metrics, and traces to understand where failures originate. This tells me whether the system lacks circuit breakers, proper timeout configurations, or back pressure mechanisms. The experiment is valuable because it reveals hidden coupling and brittle assumptions. The goal is not to blame the latency, but to redesign the interaction to be more tolerant of it. Final question for this section. Is it ever irresponsible to run chaos experiments in production? Pause here. A mature answer would sound like this. Yes, it can be irresponsible if done without preparation. If you lack observability, rollback plans, or stakeholder alignment, injecting failure can cause unnecessary harm. Production chaos should be controlled, scoped, and monitored. You need clear blast radius limits and a way to abort quickly. However, avoiding production experiments entirely can also be irresponsible because it gives a false sense of confidence. The balance is careful design, communication, and incremental rollout. Chaos engineering is not about recklessness. It is about disciplined, hypothesis-driven resilience testing. Next question. How would you design a safe chaos experiment in a high-traffic production system where downtime is extremely costly? Pause and answer. A strong candidate might think through it like this. In a high-traffic production system, I would first narrow the blast radius. Instead of targeting the entire fleet, I would scope the experiment to a small percentage of traffic, maybe a single availability zone, or a small subset of pods behind a feature flag or weighted load balancer. I would define a very clear hypothesis, such as if one instance in this group fails, error rate should remain below a defined threshold. Before running anything, I would ensure observability is solid. That means having real-time metrics on latency, error rate, saturation, and business indicators like checkout success rate. I would also define abort conditions in advance. For example, if error rate exceeds a certain percentage for more than a minute, the experiment stops automatically. I would also coordinate with stakeholders, not to get permission for every detail, but to ensure on-call engineers and business owners are aware of the test window. The goal is controlled learning, not surprise. Finally, I would run the experiment during a period of stable baseline behavior, not during an ongoing incident or a peak campaign. The design principle is progressive exposure and clear guardrails. Next question. Imagine you simulate a regional outage in a multi-region architecture, but failover takes much longer than expected. Users experience noticeable degradation. How would you approach fixing this? Pause here. A strong candidate might reason step by step. First, I would measure exactly where the delay is happening. Is DNS taking too long to propagate? Are health checks slow to detect failure? Is traffic routing policy configured conservatively? Or is there data replication lag preventing quick promotion of a secondary database? Once I identify the bottleneck, I would evaluate trade-offs. For example, reducing health check intervals can speed up failover, but increase false positives. Lowering DNS TTL can improve agility, but increase resolver load. Promoting replicas more aggressively can reduce downtime but risk data inconsistency. I would likely implement improvements incrementally. Perhaps start with tuning health check sensitivity and validating that application instances can handle sudden traffic shifts. Then test again in a controlled manner. The key is not to over-optimize one parameter blindly. Multi-region failover is a system-level behavior involving networking, data consistency, and client behavior. Fixing it requires looking at the entire chain rather than just one layer. Another question: how do you prevent chaos experiments from triggering cascading failures in tightly coupled microservices? Pause and answer. A strong answer might sound like this: I assume that cascading failure is a real risk, especially in systems with synchronous dependencies and aggressive retry logic. So before running experiments, I would assess whether circuit breakers, timeouts, and rate limits are properly configured. If a service calls another service synchronously and retries without backoff, introducing latency or failure can multiply traffic and overload upstream systems. So I would ensure exponential backoff is implemented and that there is a maximum retry cap. I would also test in isolation first. Instead of taking down an entire dependency, I might inject latency on one instance or simulate partial failure. That helps me observe how retry behavior behaves under stress. Additionally, I would monitor not just the target service but adjacent systems. Cascading failures often show up in unexpected places, such as queue backlogs or thread pool exhaustion. In short, preventing cascades is about designing for graceful degradation and understanding dependency chains before injecting failure. Next question. You run a chaos experiment that kills random pods in a Kubernetes cluster. Auto-healing works, but users still report brief spikes in latency. How do you interpret this result? Pause here. A strong candidate might think through it carefully. The fact that pods are replaced successfully means the control plane and scheduling mechanisms are functioning. However, latency spikes suggest that capacity is momentarily reduced below demand during the replacement window. I would examine how many replicas are running and what the headroom is. If we are operating close to maximum utilization, losing even one replica can create queue buildup and increased response times. I would also look at readiness probes and startup time. If new pods take a long time to become ready, the system runs under capacity for longer than expected. Another factor is connection draining. If load balancers are not properly draining connections before termination, clients may experience failed or retried requests. So the lesson is that auto-healing alone is not enough. True resilience requires over-provisioning buffers, fast startup times, and proper connection management. The experiment reveals that we may need to increase replica count or adjust scaling policies. Final question in this section. How do you measure whether chaos engineering is actually improving system reliability? Pause and answer. A mature response might sound like this. I would measure both technical and organizational signals. Technically, I would look at trends in incident frequency, mean time to recovery, and error budget consumption. If after running structured chaos experiments we see fewer surprise outages and faster recovery, that is a positive indicator. I would also track hypothesis validation. For example, before an experiment, we state that the system should recover within 2 minutes. After running the test and implementing improvements, we measure whether that recovery time decreases over iterations. On the organizational side, I would assess confidence. Are engineers more comfortable discussing failure modes? Do post-incident reviews show fewer unknowns? Is there a documented understanding of system limits? Chaos engineering is not about breaking things for sport. It is about reducing uncertainty. so success is measured by fewer unknown failure behaviors and faster, more predictable recovery when incidents occur. That concludes the deep technical portion. Pressure and judgment. Questions. Let us move into the final section. These questions are intentionally ambiguous. There is no perfect answer. I am looking for judgment, prioritization, and calm reasoning under uncertainty. First question. Your CTO asks you to introduce chaos engineering immediately because a competitor is talking about it publicly. Your system is already unstable, and your on-call team is exhausted. What do you do? Pause and think about that. A strong candidate might respond like this. I would acknowledge the business motivation, but I would push back on the timing. Chaos engineering amplifies stress in the short term. If the system is already unstable and the team is burned out, injecting failure is likely to cause more harm than learning. I would propose a phased approach. First, stabilize the most frequent sources of incidents, improve basic observability, and reduce noise in alerts. Then, introduce very small, low-risk experiments in non-production environments to build confidence and tooling. I would also be transparent with leadership about risk. Chaos engineering is not a marketing checkbox. If implemented poorly, it can erode trust internally. So my decision would prioritize team sustainability and baseline reliability before experimentation. Second question. You run a controlled failure injection in production within a small blast radius. Unexpectedly, it triggers a chain reaction and causes a brief but visible outage. Leadership questions your decision. How do you respond? Pause here. A mature answer might sound like this. First, I would not become defensive. I would acknowledge the impact and take ownership for the decision. Then I would explain the hypothesis, the guardrails that were in place, and why the blast radius was considered acceptable. Next, I would analyze what assumption was wrong. Did we underestimate dependency coupling? Were our abort thresholds too slow? Was there hidden shared infrastructure that expanded the blast radius? The key is to convert the incident into structured learning. I would document what failed in our assumptions and propose improvements before running further experiments. I would also clarify that the goal of chaos engineering is to surface weaknesses before customers experience them unpredictably. The temporary outage is undesirable, but if it reveals a systemic fragility that could have caused a larger outage later, that context matters. The tone would be calm, accountable, and forward-looking. Third question. Your organization operates a high-revenue system. Legal and compliance teams are concerned that deliberate failure injection could violate contractual uptime commitments. Do you stop chaos engineering entirely? Pause and consider that. A thoughtful candidate might respond this way. I would not stop entirely, but I would adapt the scope. Chaos engineering does not have to mean taking down core services in peak hours. It can include injecting latency and shadow traffic, isolating staging environments that mirror production, or running experiments during low traffic windows. I would work with legal and compliance to understand the exact contractual constraints. Some agreements allow limited maintenance windows. Others focus on monthly availability percentages rather than minute-by-minute uptime. Based on that, I would design experiments that respect contractual obligations, while still testing resilience. For example, instead of killing an entire service, we might simulate dependency failure in a canary region serving a small percentage of users. The principle is not rigid ideology, it is responsible risk management aligned with business constraints. Final pressure question. You have evidence that your system cannot handle the loss of a critical dependency. Fixing it properly requires months of architectural work. Leadership wants to accept the risk for now because the failure is considered unlikely. How do you handle this? Pause here. A strong answer might go like this. I would quantify the risk as clearly as possible. What is the probability of failure based on historical data? What is the estimated blast radius if it occurs? What is the potential financial and reputational impact? Then I would present options. Full architectural redesign might take months, but are there mitigations that reduce risk in the short term? For example, adding rate limiting, caching, partial failover paths, or manual runbooks. If leadership still chooses to accept the risk after understanding the impact, I would document that decision explicitly. Risk acceptance should be conscious and visible, not accidental. At the same time, I would advocate for at least incremental improvements. Total inaction is rarely necessary. Often there are smaller resilience gains that can be implemented quickly while larger redesign efforts are planned. The maturity here is recognizing that engineering decisions exist within business realities. My responsibility is to surface risk clearly, propose mitigations, and ensure decisions are informed rather than reactive. That concludes this interview simulation on chaos and failure injection. Take a moment to reflect. Which question made you uncomfortable? Was it the one about pushing back on leadership, the one about triggering an unintended outage, or the one about accepting architectural risk? In real interviews, these are the moments that differentiate strong candidates from average ones. Not the definition of chaos engineering, but the judgment behind when and how to use it. If you are preparing for DevOps, SRE, or platform engineering interviews, do not just memorize tools. Practice explaining trade-offs. Practice acknowledging uncertainty. Practice articulating risk in business language. Before you move on, pause the video and answer the pressure questions out loud. Compare your reasoning with the sample responses. Notice where you might have focused too narrowly or missed stakeholder considerations. If you found this useful, subscribe so you do not miss the next interview simulation. Each session focuses on a different real-world theme that often appears in senior-level interviews. And as always, the goal is not perfection. It is clarity, structured thinking, and calm decision-making under pressure. I will see you in the next one.